we had started taking a look at the phenomena of superconductivity, which is a phenomena in which if you measure resistance as a function of temperature, then below a certain temperature which is called as a superconducting critical transition temperature, the resistance goes very low. It goes below measurable values and typically it is considered it goes to the zero resistance state. So, the resistance of the material becomes very low. So, if you make a magnet by winding a solenoid with this wire and you send a current into this solenoid, the current that you send in can be sent with 0 voltage, or the power that you require to send in the current in this, which is I square R, will be 0 because resistance is 0, voltage is 0, or power required to send in the current is 0. So, if you make transmission lines with these wires, you actually can send current without any power, and this would make our power very cheap. But of course, you need to cool them down, and that is a bottleneck, technological bottleneck, as how do you transmit powers from a power grid to your home using superconducting wires, and room temperature superconductors as of today are still not available. You have to cool them down to make them superconducting. Furthermore, you can however make magnets. If you take a solenoid and you wind a wire of superconducting material and make this solenoid, send in a current with 0 voltage, you can send in current and you can generate a magnetic field, and you take away a power supply, the current will remain in that circuit indefinitely, that is the persistent current, and there will be a magnetic field which will be maintained in that coil, and these are used typically in MRI magnets which you will find in hospitals and so on. So, this is the phenomena of superconductivity, but resistance going to 0, is that the true test of superconductivity? It turns out that there is a much more basic way of looking at superconductors, a much more basic property of superconductors, and that is the following, and that goes by the name of Meissner effect. What is the Meissner effect? You can take a normal metal and you can apply a magnetic field to it and you can cool it such that it becomes superconducting. So, there is a superconducting transition temperature of the metal which you have determined by measuring the resistance as a function of temperature, and basically you look at the behavior of this metal which is superconducting, how does it behave in the presence of a magnetic field. So, you have a normal metal, you apply a magnetic field at some high temperatures above its Tc and cool it below its superconducting transition temperature. What you will find is that when the material becomes superconducting, it expels all magnetic flux from within its interior. Whatever field was present inside the material is completely thrown out. It gets completely expelled from interior of the metal. You can do the experiment in another way. You take the normal metal at T greater than Tc in a 0 applied field. You do not apply any magnetic field, which is this, and then you cool it below Tc, it becomes superconducting, namely its resistance R is equal to 0, this is also R is equal to 0, and then you apply a magnetic field to this. You apply a magnetic field to this once it is superconducting. In this particular case, the material you had applied a magnetic field above Tc and then cooled it below Tc. Here above Tc you do not apply any magnetic field, you make it superconducting and then apply a magnetic field. Here too also it enters into a completely, there is no magnetic field inside the sample, all magnetic field is thrown out from within the sample. So, this property is called as diamagnetism. You have come across this, that whenever a material, if you apply a magnetic field to it, it will actually try to shield the magnetic field from its interior. It will not allow the magnetic field to enter into the metal, and you have come across this in smaller ways in when you have looked at the Faraday effect, Lenz's law, that if you take a metal ring and if you try to apply a magnetic field, then it tries to oppose the change in flux by setting up currents which will apply a field which is opposite to that of the applied field. So, it will prevent the change in flux by setting up currents. Okay. However, superconductors are the ultimate limit of diamagnetism. They set up such strong shielding currents that they make the applied field completely 0, and it does not depend on whether you have applied the field above Tc and then cooled it down and then apply, I mean the field is continuously maintained whether above or below and you just cool it down, or there was no field applied, you cooled it down and then applied the field. In either cases, irrespective of the path taken, you will enter into this perfect diamagnetic state. Perfect diamagnetism is when the field or the local field, magnetic field inside the sample is perfectly 0. Irrespective of the applied field, the magnetic field which is present inside the sample is completely 0. And this is a typical character of superconductors. Any superconductor will exhibit perfect diamagnetism. Namely, if you apply a magnetic field, it will throw away all the magnetic field from within its interior. And this is the Meissner effect. And as the Meissner effect was shown to be path independent, does not matter in which way you have applied the magnetic field, whether above Tc you applied the magnetic field and then cooled the sample below Tc, or you cooled the sample first and then applied the magnetic field. Either ways you will enter the perfect diamagnetic state of the material. So, you reach a unique state of the superconductor irrespective of the path, and this is the true test of superconductivity. This is taken as the true test of superconductivity, namely perfect diamagnetic state which is a B is equal to 0 state. The field inside the sample is 0 when applied field is non-zero, and this state is reached irrespective of the path, and this more than resistance going to 0 as a function of temperature below Tc. The Meissner effect is taken as the true test of superconductivity. So, B is expelling of magnetic field from interior of a superconductor is the true character of a superconductor. So, any superconductor, if you apply a magnetic field to the superconductor, it will throw out magnetic field from within its interior. So, any superconductor, if you want to know if it is a superconductor, then below Tc you should observe the Meissner effect. Let us look at this perfect diamagnetic state, which is B is equal to 0 state a little better. Why is it called as a perfect diamagnet? Magnetization is B minus H. You know this from electromagnetic theory, that the magnetization is B minus H, and getting to a B equal to 0 state implies M is equal to minus H. This is the applied field, M is equal to minus of H. The magnetization in the sample is minus the applied field. It completely opposes the applied field, and as a result inside the sample the net magnetic field becomes equal to 0. And the magnetic susceptibility chi is dm by dh. So, if you put that in here, you will get that the susceptibility of the superconductor is minus 1. So, superconductors have susceptibility of minus 1. This is the maximum value of susceptibility. This is the maximum value of diamagnetic susceptibility. Diamagnetic susceptibility cannot exceed minus 1. They have to be, susceptibility has to be less than or equal to minus 1, and superconductors are the only materials which exhibit this maximum value of susceptibility, and hence they are said to be in the perfect diamagnetic state. No other material can reach such high values of susceptibility. Typical metals have susceptibilities which are in the range of 10 raised to minus 4 to 10 raised to minus 5. You can see that the susceptibility of superconductors is orders of magnitude. It is almost 10 raised to 4 to 10 raised to 5 times the susceptibility of a ordinary normal metal. So, they have huge susceptibilities, and they have the ideal value of susceptibility which can be reached, and that is why you say that superconductors exhibit perfect diamagnetism, and this is the true character of a superconductor. whereas R is equal to 0 can be exhibited by metals if they become a perfect metal, no collisions. But of course, a metal will not be able to exhibit perfect diamagnetism. Perfect diamagnetism is exhibited only by superconducting state, and you can explain this only quantum mechanically, which we will not be able to get into as a part of this course. However, you should remember that for a superconductor, perfect diamagnetism is the true character and signature of superconductivity. Now, because of this perfect diamagnetism and the large diamagnetism that one has, it leads to strange effects. One of the effects is the levitation effect, where you can take a superconductor and you can take a magnet on top. So, you have a magnet which is placed on top of a superconductor, and the superconductor does not allow the magnetic field to enter into the superconductor because of the Meissner effect or perfect diamagnetism. B is equal to 0 inside the material. As a result, it will expel all magnetic field from the magnet which is applied to the superconductor, and as a result the magnet actually floats on top of the superconductor. Rather than the magnetic field penetrating and passing and magnetizing the superconductor actually opposes the magnetic field, and as a result you can think of the superconductor, if the magnet has a north and south pole, this is the magnet, you can think of the superconductor as having developed an equal pole. So, this magnetic field will be opposed. It will try to oppose whatever is the applied field from this magnet, it will oppose it by creating a similar pole. This is the superconductor, and as a result you know that two similar pole magnets repel each other and they can actually be made to float on top of each other, and it actually creates the levitation effect. And there is a nice movie on the internet which you can check of levitation associated with superconductors, and that movie I show you here. So, this is a superconductor and now you are placing a magnet on top of the superconductor, and what you see is that the magnet is floating on top of the superconductor. You can see that there is nothing in between. This magnet is floating on the superconductor. You can think of this end as the north pole and this as the south pole. It is giving magnetic field from the magnet. This is your magnet, and this is your superconductor which has been cooled to T less than Tc, and this magnet in the presence of this external magnetic field is generating an equal pole of north pole and south pole. This is generating an equal field on the other end. So, this is opposing the externally applied field so that these fields are balanced out, and because of these two repelling entities, if you adjust it properly, you can balance the magnet on top of the superconductor, and this is called as the levitation effect. So, you can balance a magnet on top of a superconductor and have no friction, no contact between the two surfaces, no contact between two surfaces. So, people have thought of trains called the maglev train, where you can have a train which has a magnet which is floating on a rail which is made of superconductors, and you can have the train which is never going to touch the railway line, and it can go to extremely high speeds. And this has actually been tried out in Japan, and they actually break the speed of sound and they go extremely fast, but because of safety issues it has not been implemented they have been remained as research prototypes and they have not been implemented. But superconductivity leads to perfect diamagnetism, and the perfect diamagnetism leads to this strange and exotic phenomena of levitation.